Welcome back, everyone. We are going to finish up chapter 7 here. So far in sections 1, 2, and 3, we have found a confidence interval for a mean. We have found it using z interval or t interval, depending if the population standard deviation was known or not. Then in section 3, we did a confidence interval for a proportion, and the proportion was we used one prop z interval, and so those are our two so far. Let me write those down. So far we have found a confidence interval for mu. We found one for the true proportion p, and now finally we are to the standard deviation or variance. We'll find both actually. And so that is our focus today. Unfortunately, our calculators don't have a program already set up for this. So we're gonna have to do these by hand, which is why I have a separate video for them. Before we get started, you will need to download and have a chi-squared distribution table. Your teacher may provide you with one, or if you just type in chi-squared distribution table into any web browser, hundreds will come up, and most of them will probably work just fine. But I will be referring to this eventually, so we'll come back to that. But please make sure that you have that downloaded. If you need to pause the video to go find that and have that available, that is fine. We are moving on. When constructing a confidence interval estimate of the population standard deviation, we construct the confidence interval using the chi-square distribution. So we have a new distribution that I just sort of introduced you to a second ago. It's a Greek letter chi is how I pronounced it. Distribution. It's often written like this, chi-squared. And this is what we use. What's a few things that are different about a chi-squared distribution is, first of all, it's not symmetric. You see that's the first bullet down there. In fact, if anything, it's skewed right. If you remember, skewed right means that we have a longer right tail. Chi-squares can be 0 or positive. So you'll notice that we start here at 0. There are no negatives, unlike the t or the z distribution where we go from negative infinity to infinity and so on. It does go off to positive infinity. However, it does start at 0. Chi-squared distribution is different for depending on the degrees of freedom, and the degrees of freedom for a chi-squared distribution is n-1. As the number of degrees of freedom increases, the chi-squared distribution approaches a normal distribution. So it starts looking like a normal bell curve if we get n high enough. All right, let us practice a little. So we're going to figure out how to find the critical values of chi-squared. And we're going to start with a confidence level of 95% and n is 22. What that means for us is that our degrees of freedom is 21. Or it's n-1. And I'm going to draw a little picture here. Start at 0. This is my chi-squared. And to find these critical values, and this one is 95%, so 0.95 goes here. That leaves us with 5% left, and that gets split in half. So half of 5% is 0.025, and half of 5% here is 0.025. And we are looking for chi-squared left and chi-squared right. And we will need the table for that. Before we do that, I want to make it clear that starting here, a chi-squared distribution table only uses area to the right. So how much area is this to the right of my chi-squared left? Well, that's 0.95 plus 0.025, which is 0.975. And my degrees of freedom in this case are 21. So 0.975 degrees of freedom is 21. Let's go to our chi-squared distribution. So I'm going to go to 0.975. That is up here. We are at 21, and those two are going to connect right there. There is our critical value, 10.283. So this is 10.283. And the area to the right of the chi-squared r is just 0.025. So we'll go back to 0.025. So we're going to go over here. 0.025 is up here. And these two collide right here. Degrees of freedom is 21, so we're at 35.479. Oops. So this is 35.479. So you may need to practice this a little bit, which is totally understandable. All right, now we're going to find the chi-squared critical values. And now we're going to be dealing with a 99%, the sample size of 25, which means for us, our degrees of freedom is 24, n minus 1. So again, skewed right. And because in the middle is 99, that means that each of our little areas here is a 0.5%, 0.005. Same here, 0.005. And here's again our chi-squared left and our chi-squared right. Now I want to again be clear. The area to the right of my chi-squared left is 0.99 plus 0.005, or 0.995, degrees of freedom of 24. All right, so we are looking here. Degrees of freedom of 24 is way down here. So I'm looking right there, 9.886. And the area to the right of my other one is 0.005. That is going to be way over here. So we are down here at 45.559. Little cramp there. But again, hopefully you can find what you need with this. So that's how we find the critical values. Now this is going to be one step in that we're going to need so that we can find the confidence interval, which we're going to talk about right now. Constructing a confidence interval used to estimate a population, standard deviation, or variance, and here are the requirements. It has to be normally distributed. We have to know that it's normally distributed, otherwise what we're doing won't work. All right, if we want the population standard deviation, then we're going to be using this formula. And you can see we need those critical values to be able to do that. Now for the variance, it's the exact same formula, but no radicals. And the variance is sigma squared. So you can see once you have one, you can just take the square root and get the other. And I'm actually going to take advantage of that here in just a moment. All right. Here's our first example. A study of life expectancy showed that a random sample of 6 states had a standard deviation of 0.9 deaths this year per year. So this is our S. Find a 90% confidence interval of the variance and the standard deviation. And we have all the bells and whistles. We'll go to 1 decimal place. Okay. So here's what's going to happen. I'm first of all going to draw our chi-squared distribution so that we can find the critical values. Chi-squared. And this is a 90% confidence interval, which means we have 10% left over, which means there's going to be 5% in each of these. So we need our critical value left and our chi-squared right. So I want to point out that n in this case is 6, which means our degrees of freedom is 5. And keeping in mind in the middle here is 0.9. So once again, for this first one, this is going to be 0.9 area to the left, to the right, plus 0.05, which is 0.95. So 0.95 with degrees of freedom of 5. Go back to my table. We are now here and 0.95 here, which brings us to 1.145. And we will need that value here in just a moment. For the second one, the area to the right is the 0.05. .05 is right here, and that collides right there, 11.071. Double check that. 71, okay. All right, so let's go back to our formula now. So I'm going to do the variance first, and then I'm going to show you with the calculator how we can do that. So n minus 1 is 5 times sigma, or the standard deviation, 0.9 squared over 11.071. I know it looks like it's backwards, but it really isn't. So let's see what we get here. So 5 times 0.9 squared divided by 11.071. And they want us to round it off to the nearest decimal. So I'm going to go to 1 decimal point. That'll be 0.4. And I'm going to get the value right below it by taking the square root of this. So square root of the previous answer. So that's going to give me down here 0.6. All right, let's do the other one. So 5 times 0.9, oops. 5 times 0.9 squared divided by 1.145. And that's going to round off to 3.5. And I'm going to take the square root of that, second square root, the previous answer. And that's going to be 1.9, it looks like to me. Not too bad. Hopefully it's not that big of a deal for us. All right, we have two more examples. A psychologist wants to estimate the standard deviation of IQ scores. It is widely believed that IQ scores follow a normal distribution. Her random sample of 29 IQ scores, let's write that down, n equals 29, which means my degrees of freedom is 28, and has a mean of 103, which we won't use, and a standard deviation of 18.2. Find the 95% confidence interval for the population standard deviation based on this sample. All right, so they want 2 decimal points afterwards. Here we go. And they only want the standard deviation for this one. So let's draw our little and I'm going to split up our alpha. Alpha in this case is 5%, so half of 5% is 2.5%. In the middle here is 0.95. And for our first one, it's going to be 0.95 plus 0.025, 0.975. So we have degrees of freedom of 28 and 0.975. So we are now down here. Oops. Degrees of freedom is 28 and 0.975. 28 is down here. 0.975 is up here. So it looks like we are colliding right there. 15.308. And area to the right of the right one is 0.025. .025 is here. And they're going to meet right there. 44.461. All right, so let's get our standard deviation. So this is going to be the square root of n minus 1, which is 28, times the standard deviation, 18.2 squared, over the right one, which is 44.461. Eight, 18.2 squared over the other one, which is 15.308. So 28 times 18.2 squared divided by 44.461. Square root of that. I'm getting about 14. Wait, they want 2 decimal places, so we'll go 443. Why not? The other one, I'm going to start with the square root. 28 times 18.2 squared divided by 15.308. I'm getting 24.6145. There it is. So you'll really need to practice with your calculator. Make sure you know how to use it and where everything is and all that. All right, that brings us to our last problem. Now, I've already loaded these values into my calculator. You can see the 433, 446, and so on. So you may need to pause this video and put those values into there. And the reason we need to put them into the calculator is because I need, and before I even do that, let's read the question real quick. The scores on an examination of economics are approximately normally distributed with a mean of about 500 and an unknown standard deviation. The following is a random sample of scores from this examination. Find a 90% confidence interval for the standard deviation. All right, before we get going, I'm going to run one var stats on this data because I need the standard deviation. So I'm going to go to stat, calculate up at the top, one var stats, and we get an advertisement. All right. My data is in list 1. If yours is in a different list, you'll need to change it to that list. We don't need anything in the frequency. But what we do need after we hit go is the standard deviation that you see right there. So I'm getting that SX, which is my sample standard deviation, is about 63.389. I'm going to need to use that data in a moment, but first I need to find my critical values. By the way, just real quick, n in this case is 6, which means my degrees of freedom is 5. We're looking for a 90% confidence interval. That leaves 10%, and so half of that is 5%. And the other 5% goes right there. My chi-squared left, chi-squared right, and right in the middle is 90%, 0.9. So for my first one here, again, that is going to be 0.9 plus 0.05, which is 0.95. So I need 0.95 with a degrees of freedom of 5. So 0.95 and degrees of freedom of 5. Whoop. All right, so degrees of freedom is 5, and 0.95 is over here. We actually found these earlier today. That's fine. 1.145. And for the right one, we have 0.05. Degrees of freedom is 5. Oh, I didn't highlight before. 0.95, that was the previous one. So now we're doing the opposite. And we are at 0.05. That's going to collide right there. 11.071. All right, so this gets us to the square root of 5 times 63.389 squared. So we do that, 389 squared over 11.071. Over 1.145. All right, here we go. So second square root, 5 times 63.389 squared divided by 11.071 gets me 42, and they want us to round it to at least 2 decimal places. So it's 42 point, we'll say 60. And then the other one is going to be the square root of 5 times 63.389 squared divided by 1.145, 132.4 0.46. That is our final answer. I hope that you found this useful.